Hello, my name is Muhammad Ayman from Kate 1. Let's move to the video about plutonium. Today I will show you an element used to make a nuclear bomb. Discovery of plutonium, element 94 on the periodic table, was first discovered in 1940 by American scientists Glenn T. Seaborg, Edwin M. McMillan, Ralph A. James, and Albert Ghiorso at the University of California, Berkeley. Plutonium was synthesized by bombarding uranium-238, U-238, with deuterons hydrogen nuclei containing one proton and one neutron using a cyclotron.
The Manhattan Project. Plutonium is considered highly dangerous for several reasons, primarily due to its radioactive properties and potential for use in nuclear weapons. Plutonium played a crucial role in developing the atomic bomb during World War II.
The Manhattan Project, a top-secret U.S. government research and development program, was responsible for creating the first atomic weapons.
Production and use in atomic bombs. The first atomic bomb, Fat Man, dropped on Nagasaki, Japan on August 9, 1945, used a core of plutonium-239, Pu-239, in its explosive device. Plutonium was used as an alternative to enriched uranium-235, U-235, in atomic bombs. Post-World War II period. After World War II, the US and Soviet Union continued to develop and expand their nuclear arsenals, which included the production of plutonium for nuclear weapons.
Here's what happened to the people that touched the Demon Core. The Demon Core was a 6.2 kilogram sphere containing a subcritical mass of highly radioactive plutonium created by the United States military as a component of nuclear weapons development. It was so dangerous that it killed two different scientists involved in its testing in 1945 and 1946, Harry Dalian and Louis Slotin. Harry Dalian was 24 years old during a criticality accident that exposed him to a lethal blast of neutron radiation from the core. He received 200 rads of neutron radiation and 110 rads of gamma radiation, killing him as a result of radiation poisoning 25 days later. Louis Slotin got it even worse in his criticality accident. After being directly exposed, he received 1,000 rads of neutron radiation and 114 rads of gamma. He survived for only 9 painful days. Knowing the second the blast hit that he was doomed, he calmly remarked, "Well, that does it," accepting his fate.
Plutonium atomic structure. The atomic number represents the number of protons in the nucleus of a plutonium atom. In the case of plutonium, there are 94 protons. The atomic mass of plutonium varies depending on the specific isotope of plutonium. The most common and stable isotope is plutonium-239, Pu-239, which has an atomic mass of approximately 239 atomic mass units UU. Electronic configuration of plutonium. The electron configuration of a neutral plutonium atom, Pu, is based on its atomic number. Plutonium has a complex electron configuration due to its relatively large number of electrons. The position of plutonium in the periodic table. Symbol. Atomic number 94. Group. Actinides. Group 15. In the F block. Period 7, 7th period. Plutonium is a member of the actinide series, which is a group of elements in the F block of the periodic table. These elements are characterized by their radioactive nature, heavy atomic masses, and similar electron configurations. Plutonium is positioned between uranium-U with an atomic number of 92 and americium-Am with an atomic number of 95 within the actinide series. It is a synthetic element, meaning it is not found in significant quantities in nature and is typically produced in nuclear reactors or particle accelerators. Plutonium's placement on the periodic table reflects its atomic structure and properties as a heavy radioactive element. Plutonium's chemical properties. Radioactivity. Plutonium is highly radioactive, with all its isotopes undergoing radioactive decay. This decay releases alpha particles, beta particles, and gamma rays. Oxidation states. Plutonium can exist in various oxidation states, but the most common are PuIV and PuIE and PuII, which are important in its chemical reactions. Reactivity. Plutonium is highly reactive, particularly when it's in finely divided form or as plutonium hydrides. It can react with air and water, forming oxides and hydrides. Complex chemistry. Plutonium chemistry is intricate, involving the formation of a wide range of compounds and complexes. Actinide chemistry is a specialized field that studies these properties.
Plutonium's physical properties.
State. Plutonium is typically found in the solid state. It can exhibit multiple allotropes, with the D phase being the most stable at room temperature. Density. Plutonium is a dense metal. The density varies depending on the isotope, but for Pu-239 it is approximately 19.86 grams per cubic centimeter GeoChem-free. Melting and boiling points. The melting point of plutonium varies with its allotrope but is generally around 640 dC 1184 def, while the boiling point is approximately 3235 dC 5855 dC. Plutonium appears in various colors depending on its allotrope. The D phase is silvery, while the A phase has a metallic silver-gray appearance. Magnetic properties. Plutonium exhibits unusual magnetic properties. It can be paramagnetic or antiferromagnetic depending on temperature and structure. Mechanical properties. Plutonium is a relatively soft metal, and it can be cut with a knife in some forms. It is malleable and ductile. Thermal properties. Plutonium has a low thermal conductivity, meaning it does not conduct heat well.
Bonds. Covalent bonds. Plutonium often forms covalent bonds, where electrons are shared between plutonium and other elements. This is particularly common in plutonium compounds with nonmetals, such as oxygen, where covalent bonds are formed in plutonium oxides, e.g. plutonium dioxide, Pu2. Ionic bonds. In some cases, plutonium can form ionic bonds with other elements. For instance, in plutonium compounds like plutonium chloride, Pu4, plutonium, takes on a specific oxidation state, often Pu, IEI, or PEIV, and forms ionic bonds with chlorine. Metallic bonds. Plutonium is a metal, and metallic bonds dominate in metallic plutonium or plutonium alloys. The electrons are delocalized and shared throughout the crystal lattice in these materials, giving metals their characteristic properties like electrical conductivity and malleability. Coordination bonds. Plutonium compounds can also form coordination bonds, which involve the interaction of plutonium with other elements through the donation of electron pairs, commonly with ligands such as oxygen or other atoms. Application: nuclear weapons. Plutonium is a critical component in producing nuclear weapons, such as atomic bombs. Plutonium-based nuclear bombs have been developed and tested during the mid-20th century. The potential for use in nuclear weapons is a major concern, leading to strict controls and international agreements on its production and use. Nuclear reactors. Plutonium is used as a nuclear fuel in certain nuclear reactors, including fast breeder reactors. In these reactors, plutonium-239 can undergo fission, releasing energy. This application is mainly for electricity generation and can potentially reduce nuclear waste by recycling fuel. Radiography. Plutonium sources have been used in industrial radiography for inspecting welds, pipelines, and other structures. However, its use is declining due to safety and environmental concerns. Spacecraft power sources. Plutonium-238, Pu-238, has been used in radioisotope thermoelectric generators, REAGs, to power spacecraft and deep space probes. These generators convert the heat produced by the radioactive decay of Pu-238 into electricity. Notable examples include the Mars rovers and spacecraft like the Voyager probes.
Mungkin secara sekilas kamu akan melihat foto ini seperti seorang pria biasa yang memegang sebuah kotak kecil. Namun tahukah kamu apa yang dipegang oleh pria tersebut? Ternyata kotak ini pernah meluluhlantahkan kota Nagasaki pada Perang Dunia II saat Amerika melakukan serangan balasan pada Jepang di tahun 1945. Kotak yang dipegang oleh Harold Agnew ini berisi inti plutonium yang nantinya dimasukkan ke dalam bom Fatman yang memiliki kekuatan ledakan setara dengan 21.000 ton TNT. Harold Agnew saat itu adalah seorang peneliti dan saksi sejarah pembuatan bom atom tersebut dari awal hingga akhir pembuatan. buatan. Foto tersebut diambil saat perakitan terakhir di Pulau Tinian Pasifik, yang mana tugas Andrew adalah sebagai pengukur gelombang kejut yang dihasilkan dari ledakan inti plutonium di dalam kota kecil itu. Inti plutonium inilah yang menjadi penyebab ledakan kedua dari serangan Amerika terhadap Jepang di kota Nagasaki pada tanggal 9 Agustus 1945. Foto ini menjadi bukti sejarah yang diarsipkan oleh pemerintah Amerika, serta foto ini telah tersebar di jejaring sosial seluruh dunia.
References.
Thanks for watching.